Our final speaker of the evening is Natalie Hinkle. She is a planetary astrophysicist at Vanderbilt studying the composition of nearby stars and how they may affect the makeup of orbiting planets. She observes planets outside of the solar system, or exoplanets, and has studied exotic systems where planets orbit two stars, or what life would be like on an exomoon. She got her bachelor's in physics at Oberlin College, where she rounded out her education by including dance, theater, and romantic lit, so people would talk to her at parties. She enjoys rock climbing and hiking. So please help me welcome our final speaker of the morning, Natalie Hinkle.
Thank you. All right, so my name is Dr. Natalie Hinkle, and I am a planetary astrophysicist. Now, I'll be the first to tell you that I made that title up. You see, I had to make up a title to describe what it is I actually do. So I got my PhD in astrophysics because I look at stars that are near to the sun and their properties. But I also look at planets and how those stars and planets interact with each other. But it wasn't until about 20 years ago that the term planetary scientist really only meant somebody who studied the planets in our own solar system. But it was in 1995 that the first planet outside of our solar system, or exoplanet, was discovered. And today, well, at least last week when I took this picture, there are 3,532 known exoplanets. So this field that I'm in, it is brand new. In fact, if it was a person, it would barely be older than all of you. But astronomy, which is the study of celestial bodies, is the oldest known natural science. So we're really just figuring out all the crazy things that are happening with respect to exoplanets. There are some very strange systems that are out there. For example, if my slide will go, there are planets that are so close to their stars that they have a period of 10 hours. The Earth has a period of 365 days. And there are other planets that orbit two stars at the same time, just like Tatooine. So the field of exoplanet science is really just starting to make its headway, understanding how our solar system was formed and how that compares to all these other systems. Now, I don't just look at how stars and planets move with respect to one another. Instead, what I look at is how they're chemically related. But let me explain. The Big Bang. So, after the Big Bang, the only elements that were created were hydrogen and helium. There was no carbon or oxygen or any of these other elements that are the basis of our everyday lives. So you have this hydrogen and helium that goes all over the universe, but it does so in an uneven way until it makes these massive balls of gas, and that's kind of what you're seeing right now. And so these huge balls of gas, they eventually collapse and they form the first stars. Now, when I say massive, I mean very massive. So they're about 1,000 times more massive than the sun. So that'd be like saying that our sun is a grape and these first stars was a cat, except less furry. So it was within these massive, massive stars that you finally have fusion, which has enough temperature and density that you can slam elements together, different atoms, and they stick. So you slam a hydrogen together with another one, and then you get helium, and then lithium, and beryllium, and then carbon. But these really big stars, they live fast, they die young, and then they explode all over the place. But with all the typical hydrogen and helium with them go these seeds of carbon and nitrogen. So the next generation of stars, they're again made up mostly of hydrogen and helium, but they also start off with these seeds, and from these seeds they start building heavier and heavier elements. So what you're able to get is actually the periodic table of elements. There we go. So this was created by a colleague of mine, Jennifer Johnson, and as you can see, it's color-coded to show where these different elements come from. So the blue is from the Big Bang, like I said, but there are other ones that are color-coded for low-mass stars, some are high-mass stars, and some are coming from two stars that are slamming together and exploding. So it's a certain kind of supernova. But the other things that are created at the same time as stars with all of these elements are planets. So that's everything from Mercury to Venus, even the dwarf Pluto, are all made at the same time. But it was on Earth that life blossomed, and from that life came humanity. And we are entirely dependent on the elements that are within our planet. Now, it's very easy to be a romantic when it comes to astronomy, and I could talk for a long time about it. However, I found that there's kind of like this disconnect between the philosophy of astronomy and what it actually takes to be an astrophysicist. You see, to do the science, you need to connect the observation and the explanation. There's a back and forth between the data and the theory, and you need to know both skill sets in order to do what I do. So this is an overview of what it actually takes to be an astrophysicist. So all of you are in middle school and high school, right? Thank you. Okay. All right. So after I finished high school, I was in school for 10 more years, which is intimidating, I know, but I really like solving problems, so it didn't seem like that big of a deal. So first I went and got my bachelor's degree, and I got that in both math and physics. You see, math is the language of nature, and you need the physics to take that language and look at all the different physical things around us and make predictions out of those things. And then I also, I would recommend that you study computer programming. Most of what I do is on a computer. So I ended up teaching myself how to code, but it would have been much easier had I actually taken classes. But as Riley said, I also did a number of other things. I did theater and dance, and I looked at romantic literature, which I found to be really useful. So I recommend a well-rounded education. And then after I did that, I went to graduate school, which I was there for about 6 years. Now my day-to-day life kind of varies, but I'll go over some like major themes. So I told you that I look at elements inside of stars, but what that means specifically is that I put together a gigantic database of elements inside of stars. This is HypatiaCatalog.com. All of you can go and look at it if you want. This is real scientific data. So this is my catalog. I named it after one of the first known female astronomers. And it has 72 elements within 6,000 stars, all of them within 150 parsecs, or 500 light years. So what I do is I work on the back end of this database. I also make cool plots to look at my data and try to understand it. Like I said, I spend a lot of time on the computer. But I also work with collaborators to talk to them about how they could use this science for whatever they're trying to do, and that's geologists, biologists, astrobiologists. The other thing I do is I write grants. I ask the government, specifically the National Science Foundation and NASA, to give me money to work on projects that I think are really interesting or really important. And then finally, I write papers. You might have heard of some of the different papers when scientists make discoveries. And these papers are very important because it's the way that scientists communicate the results. But it's not just the results, it's also the methods and the data, so that way people can check my work, make sure I did the right thing, but also so they can build on top of my work. Now, rather than have you read my papers, which are pretty long and in all honesty kind of boring, I'll just tell you about a few of my projects. So I mentioned Tatooine earlier because Tatooine is actually a really interesting problem. So you have one planet going around 2 stars at the same time. So the question is, what is it like on that planet? What's the temperature going to be like when sometimes you see 2 stars at once and then sometimes you just see 1 star? And what about the orbit around that? Could the planet fall into these stars and then get disintegrated? Or is there a certain regime where it's going to be stable? So I actually modeled this with a collaborator of mine. The blue dot is the planet. The 2 dots in the middle are the stars. And the white is what you're seeing is the habitable zone. You might have heard of it called the Goldilocks zone, where you'd expect to find water. So what you can see is that this planet is going all over the place. The orbit is really eccentric. This is nothing like what we see in our own solar system. And today, there are 19 of these. They're called circumbinary planets, which is pretty cool. Now, I mentioned to you earlier that stars and planets are made at the same time. So this is really important to know because you can assume then that what is in the star is also in the planet. And like I said, this is important because even with the best technology and the newest satellites, we scientists, anybody, cannot see to the surface of a planet outside of our solar system. It's just not possible. We can see through some of the atmospheres, sure, but we can't go and take a scoop of the planet and say what it's like to be on the surface of the planet. or what it's like to have the different tectonics or volcanoes or anything like that. We just can't look at that. So one thing I do is I work with a geologist to make fake planets to see what they might be like. So we look at the mineralogy and the interior structure to see if it would be an alive planet, which would be more habitable. And then a project I'm working on right now is like Netflix, except instead of movies, it's about planets. All right, so you guys watch Netflix, right? Right, okay. So when you watch enough movies on Netflix, after a while it learns the trends that you watch. So say that you like goofy movies because everybody likes goofy movies. So it takes this trend and it applies it to the back catalog of movies you haven't watched, and it suggests movies that you might like based on this trend. I do the exact same thing, except I look at the elements that are inside of stars that have planets, and I train my algorithm to figure out what those patterns are between those elements. I then take those trends and I apply it to all the stars in the Hypatia Catalog that aren't known to host planets, and I make predictions on them. So after a number of double checks, I found out that my algorithm is about 70% correct, which is pretty exciting for me. Now, I love what I do. I really do. But I'll be honest, it hasn't been easy. In fact, my own personal path has been pretty difficult. But I figured out how I learned and how I was able to understand the concepts, and I studied really hard. And I learned a few things along the way. So when I was an undergraduate, this is me as an undergrad, I remember I took this exam, and I studied a long time. And when I took the exam, it was so hard. And I honestly, legitimately thought that I had failed. Like, I had no hope. So I got back the exam, and I got a B+. I was like, great, I can do this. And then I happened to see the exam of the person sitting next to me, and they got an A. And I immediately felt really bad about myself. I felt like I wasn't as smart. I felt like I wasn't as capable. And then I took a step back, and I was like, what am I doing? I just went from feeling really good about myself to really bad, just because I saw what they got. So then I realized I have to stop comparing myself to other people. I can't ask what they get. I can't look at what their exam scores are. I need to define my own metric, my own grade, that I'm going to be happy with. And I need to define it based on how hard I've worked. You see, everybody at some point in their life is going to be challenged. That's a fact. So it's an important skill to learn, to work hard, fail, pick yourself up, and then keep trying again until you do succeed. Graduate school was a little different. This is me in graduate school. So I worked on this project, and I discovered something really big. But for whatever reason, people didn't really want to listen to me. In fact, they suggested that I drop the project altogether and lose years of my life that I had spent working on this. And I thought about it, but I thought what I did was important, and I thought I was right. And I checked myself, and I was like, no, I believe in what I'm doing, so I'm going to stay with it. But instead, what I did was I changed the way I was communicating to other people. I changed their perspectives so they could see what I was seeing. And then people started listening to me. And they said I was right. And they confirmed that I had been right the whole time. And so from there, I was able to get my self-confidence. Here I am now. Yeah, I'm pretty cool. Battles won, but also a few scars. But you know what? That's okay. Because at the end of the day, I get to do some amazing things. I've traveled all over the world. I've been to 20 different countries. And I've got to work on wonderful telescopes and meet incredible people. I get to look at a huge amount of data and discover new methods to look at it that nobody's thought of before. I get to zoom from the Earth into outer space and see not just pictures and numbers and data, but see questions and possibilities and actually get to work on how to answer them. And I get to do all of this not just because I'm smart, but because I worked really hard. I believed in myself, and I didn't give up. And if I can do this, so can you. But just in case, this is my email and my Twitter. Feel free to get a hold of me if you ever need anything. Thank you.